In this lesson, we want to review radical expressions. So in the last lesson, we reviewed rational exponents, which are also known as fractional exponents. Now, I want you to recall these allow us to convert between radical notation and exponential notation. So what we want to do is just quickly recap that process because we're going to need that operation for our lesson today. So if we have something like the nth root of a, we should recall that we can write this in exponential form by basically taking the radicand a and writing that as the base of our exponential expression. And so a will be raised to the power of 1 over the index. In this case, the index is n, so 1 over n. So if I had something like, let's say, the square root of 4, this has an implied index of a 2. So essentially, in exponential notation, I just take this 4, and I say it's raised to the power of 1 over, again, the index is 2, so 1 over 2 or 1/2. So we know that taking the square root of a number is like raising it to the power of 1/2. Similarly, if we take the cube root of a number, it's like raising it to the power of 1/3. So something like, let's say, the cube root of 27, this would be equal to, the 27 here is the base of the exponent, and it's raised to the power of 1 over 3. Now, we have another rule which we're going to rely on heavily throughout our course. If you have the nth root of a, and let's say a is raised to a power now. So a is raised to the power of m. This is equal to, this part's the same. We're just going to have a raised to the power of m over n. So everything's the same except for the fact that you have an m in the numerator now over your n, your index, in the denominator. Now you might also see this written in a different form. You could also say this is the nth root. Let me make that n a little better. So the nth root of a, and this whole thing is raised to the power of m. And essentially because of the power to power rule, you could really write this as a raised to the power of m over n as well. But essentially for this lesson, we're going to deal with this scenario. So we don't really need to worry about this. We just want to reference it maybe later on if it comes up. So we can use this rule to kind of simplify here. I want you to realize that 4 is nothing more than 2 squared. Right? So we know the square root of 4 is 2 because 2 squared is 4. But to simplify this using exponents, we can say the square root of 2 squared like this. And we'll go ahead and say this is equal to, we have 2, which will be raised to the power of 2 over 2, which is basically 2 raised to the first power. So I want you to realize that in most cases, you're going to be able to cancel an exponent here with an index here. We'll see later on in the lesson that when you have a negative involved there and you have an even index, you need to kind of think about what's going on first. But in general, you can just cancel between here and here if your number here is non-negative, okay? So we'll talk about the exception later on in the lesson. So as this one goes, we have the cube root of 27. We know 27 is 3 cubed, so I could write this as the cube root of 3 cubed. And again, if I wanted to, I could cancel this with this. But I'm going to show that process with exponents. So I can say this is 3 raised to the power of 3 over 3. So this exponent over this index, and this is equal to 3 over 3 is 1. So 3 to the first power, or just 3, right? And here I could just really write this as 2. All right, so the purpose of this lesson is to give a basic overview of radical expressions. Most of you, or if not all of you, understand how to take the square root, the cube root, the fourth root of some number. But it's important to kind of go back and make sure you understand all the vocabulary and all the different scenarios that we're going to encounter throughout the course. So we'll start with something very basic. We're going to show the parts of a radical. So if you have the nth root of a, the n right here is known as the index. And for a square root, the index is left blank. So if you have a square root, it's implied to be a 2, right? So something like, again, the square root of 4. You don't show a visible index, but it's known or understood to be a 2. But if I have a cube root, a fourth root, a fifth root, some higher level root, I need to make it clear that I have that level, and so I want to put a visible number there. So if I have the cube root of 8, I want to make sure to put a 3 there to identify that this is a cube root. Okay, so very important that you do that. Then this guy right here, this number or variable or expression that's underneath the radical symbol is known as a radicand. And then the symbol itself is just called a radical symbol. Radical symbol, okay? Then when we talk about the whole thing together, it's just known as a radical. So when I say a radical, I'm talking about all parts of this together. So what does a radical allow us to do? Well, we know about taking a number to a power. And essentially, when we have a radical expression, it's reversing the operation of raising to a power. So just like addition and subtraction are inverses, multiplication and division are inverses, you have radicals that are inverses with kind of raising to a power. So it basically asks the question, what number raised to the index is equal to our radicand? So in this case, we have the square root of 49. So I'm going to put a visible index of 2 here just for our demonstration purposes. But again, you don't need that. And essentially, I'm asking what number, so let me write this out, what number raised to the power of the index, and the index in this case is 2. So what number raised to the power of 2 gives us the radicand, which in this case is 49. So that's the question we're asking each time. If I had the cube root of 8 as another example, I would just say what number raised to the power of 3, because my index is a 3, gives us the radicand is 8. Okay? If I had the fourth root of, let's say, 625. So it would be what number raised to the power of 4 gives us the radicand of 625, so on and so forth. So it's a very simple process to understand. Now, how do I go about figuring this out? Well, if I don't have a calculator, I need to factor. 49 happens to be a perfect square, so it's built from the product of a rational number times itself. And we'll talk more about the definition of a perfect square in a minute, but essentially when you factor 49, you only get 7 times 7, or you also get -7 times -7. So to answer this question, what number raised to the power of 2 gives us 49? It's 7, or also -7. When we work with radicals, and we have an even root, so a root that's a square root, a fourth root, a sixth root, so on and so forth, we're going to get 2 different roots. You're going to get a positive or principal root, and then also a negative root. So this guy right here, the square root of 49 written like this would just be 7, because this is the principal or positive square root of 49. Then, to notate the negative square root of 49, I just put a negative out in front. So I would say the negative square root of 49, and this equals -7. So for this guy, it's asking, what positive number squared gives me 49? That's 7, right? Because 7 squared is 49. This guy's asking, what negative number squared gives us 49? In this case, that's -7, because -7 inside of parentheses squared is positive 49. And then we have a shorthand to include both of these in one. So we put plus or minus like this, the square root of 49. This just means to give me the principal square root of 49, which is 7, and the negative square root of 49, which is -7. So I'm going to write this as plus or minus 7. Okay, so very, very compact notation there, and something we're going to use throughout the course. So what if I got something like the square root of 144, and I wanted to figure out what that was without using a calculator? What could I do? So most of you know that 144 is also a perfect square. It's 12 times 12. But if you didn't know that, you could just factor the number. So 144, you just use your divisibility rules. So this guy ends with 44. 44 is divisible by 4, right? 44 divided by 4 is 11. So that tells me the number 144 is divisible by 4. So what would it be? It would be 4 times 36. 4 is 2 times 2. 2 is a prime number, so let's just circle those. And then 36 is 9 times 4. 4 again is 2 times 2. 2 is a prime number, so let's circle those. And then we know that 9 is 3 times 3. And let me make that better. And we'll circle these 3's here. So we can see that we have 2 times 2 times 2 times 2, where you could really say you have 2 squared times 2 squared again times 3 squared. And I did this to where each number there had an exponent of 2 because we're looking for something that's squared. So now we can use our rules of exponents to write this as 2 times 2 times 3 being squared. 2 times 2 is 4, 4 times 3 is 12, so this is 12 squared. So that's one way to find the square root of a number if you don't have a calculator. It's unrealistic at this point in time to not ever have a calculator because we all have these phones in our pockets that can basically do anything. But in case you wanted to know how to do it, that's what you would do. So we would say the principal square root of 144 is 12. If I was asked for the negative square root of 144, that would just be negative 12. What about something like the negative fourth root of 625? Well, again, I'm looking for a negative number that when raised to the fourth power gives me the radicand of 625. So I know that an even number of negative factors gives me a positive. So that part would be taken care of. I know this would just be a negative. So 625, if I factored that, it ends in 5. So it would be 125 times 5. 125 is 25 times 5. And 25 is 5 times 5. So we can see this is 5 to the fourth power to get us to 625. But also negative 5 to the fourth power would be 625 as well. Because you would have negative 5 times negative 5 times negative 5 times negative 5. So an even number of negative factors would give me a positive product. Okay? So the negative fourth root of 625 is negative 5. If you got asked for the principal fourth root of 625, that would be positive 5. All right, so when we work with odd roots, like a cube root, a fifth root, a seventh root, so on and so forth, we don't need to worry about having a plus or minus there. When you have an odd number of negative factors, you get a negative result. So there's not going to be two roots here. So if we have something like the cube root of negative 64, we would just think about what number cubed, what number raised to the third power, gives us negative 64. Well, I know it's negative, right? Because negative times negative times negative would give me a negative. So I just need to work out 64 and think about the factors there. I know it's divisible by 4. It's 4 times 16. And I know 16 is 4 times 4. Now I can go through and say this is 2 times 2, and this is 2 times 2, and this is 2 times 2. But for the purposes of what we're doing, we've already found that 4 to the third power, or 4 cubed, is 64. So the cube root of negative 64 is just negative 4. What about something like the fifth root of negative 243? Well, for this guy, again, I'm looking for what number raised to the fifth power is going to give me negative 243. So think about the fact that this will be negative, and to factor 243, you've got 81 times 3, you've got 9 times 9, and this is 3 times 3. All right, and this is 3 times 3. So you've got 1, 2, 3, 4, 5 factors of 3. 243 is 3 to the fifth power, right? So the fifth root of negative 243 is negative 3. So when we work with radicals, we're basically going to have 3 different scenarios. So we should recall that our real number system breaks up numbers into either rational numbers or irrational numbers. So when you work with radicals, you're either going to have a value that represents a rational number, it could represent an irrational number, or it could represent something that is not a real number. So we'll get to the last part of that in a moment. For right now, let's talk about how you can tell if you have a rational number or an irrational number. So you've probably heard the term perfect square, perfect cube, perfect fourth, so on and so forth. So what is a perfect square? A perfect square is a number whose square root is a rational number. So if we went through kind of the first few whole numbers, let's say we had 1 squared, this is 1, 2 squared, this is 4, 3 squared, this is 9. Let's just skip a few and go to 10. 10 squared is 100. Let's skip a few more and go to 20. 20 squared is 400. So I would recommend you memorize from 1 all the way to 20, squaring those numbers. What's the result? It's something you're going to need to go back and forth with. But essentially, each of these results here are perfect squares, right? So if you think about the square root of 1, it's 1, right? It's a rational number. The square root of 4 is 2, a rational number. The square root of 9 is 3, a rational number. The square root of 100 is 10, a rational number. And the square root of 400 is 20, a rational number. So these are perfect squares because when I take the square root, I get a rational number. So if I have something like the square root of, let's say, 400, this represents the rational number 20, okay? You could also have a scenario where you have a fraction that's a perfect square, right? So it doesn't have to be limited to a whole number or an integer. You could have something like the number 1/4. This is a perfect square because the square root of it is 1/2, okay? So the square root of 1/4 is a rational number 1/2, so 1/4 is a perfect square. Now, you could expand this definition to having a perfect cube or a perfect fourth, whatever it is. For a perfect cube, you think about cubing a number. 1 cubed is 1, so 1's a perfect cube. 2 cubed is 8, so 8's a perfect cube. 3 cubed is 27, so 27's a perfect cube, so on and so forth. So if the number when I take the cube root of it, gives me a rational number, it's a perfect cube. If a number, when I take the fourth root of it, gives me a rational number, it's a perfect fourth, right? So on and so forth. Now, if I'm taking a square root of a number, and that number is not a perfect square, I have a radical that represents an irrational number. So, for example, 5 is not a perfect square. There's no rational number that I can square to get 5. So if I take the square root of 5, this represents an irrational number. This is irrational. And you can punch that up on a calculator, and you're going to get a nasty decimal. And it's a decimal that does not terminate, and it does not repeat the same pattern forever. So at some point, because you're limited in space, your calculator is either going to truncate or it's going to round, right? It's going to do one of the two, and it's going to give you an approximation of the square root of 5, but it won't actually be equal. And the way you can prove that to yourself is you can take the number they give you, and you can square it, and you won't exactly get 5. You'll just get something that's close. Then the same thing goes if I take the cube root of something that's not a perfect cube. So let's say I took the cube root of 12. 12 is not a perfect cube. There's no rational number that I can cube to get 12, okay? So that means if I take the cube root of that, it's going to be irrational, okay? So the last scenario you're going to deal with is a radical that represents something that is not real. So we know that we have imaginary numbers in the complex number system that we can use to deal with this. And we'll talk about that in a few lessons. For right now, we just need to understand this concept because it will come up a lot throughout our course. So if we take the square root of a negative number or an even root of a negative number, we get a problem. An even number of negative factors always gives me a positive. So if I try to take the square root of negative 25, I'm basically asking the question, what number squared or what number multiplied by itself gives me a product of negative 25? Well, there's no number in the real number system that does that, right? Because if you square a number and it's negative, you get a positive. If you square 0, you get 0. And if you square a positive, you keep the positive. So this is never going to happen in the real number system. So this is not real. Similarly, the fourth root of negative 625, this is not real. Now, I don't want you to get confused by what we looked at earlier. You can have a negative outside of the radical. So if I have the negative fourth root of 625, which we looked at earlier, this is just what negative number raised to the fourth power gives me 625. We know from earlier this is negative 5. These two are not the same. Notice how in this guy I have the negative inside. It's part of the radicand. Here my radicand is positive, so I'm good to go. My negative is on the outside. So make sure you understand the difference between the two because this is a common source of confusion. Now you might get in a scenario where you see an odd root of a negative number. This is allowed, right? We talked about these earlier in the lesson. We looked at some examples. Something like the cube root of negative 8, this is just negative 2. So this is a real number because negative 2 cubed is negative 2 times negative 2, which is 4, times negative 2 again, which gives you negative 8. You can raise a number to an odd power and get a negative. It's okay. Then something like the fifth root of negative 3,125, this is just negative 5. Because negative 5 raised to the fifth power would give me negative 3,125. All right, so let's talk a little bit about what happens when you work with variables. It's very important to understand that we can't take the square root or the fourth root or again, an even root of a negative number. So when you work with variables, you don't know what the variable represents. So you have to be cautious. So if I have the nth root of x, I have to say that, okay, I can't plug in a negative value if n is even, right? So if n is even, then I have to assume that x is greater than or equal to 0. Otherwise, I'm allowing for the possibility of a non-real solution, okay? So you have to be very careful, and you might not have something that's just x. You might have an expression there, which we'll see in a moment. So if n is odd, then x can be any real number. X is any real number. Okay, it doesn't matter because, again, an odd number of negative factors is a negative, so that's okay. So if I have the square root of negative 81, this is, again, not real. Not real. The fifth root of negative 32 is just negative 2. Then something like the fourth root of negative 2,401, this is a 4. This is a negative here. Can't take the even root of a negative number. This is not real. Okay, not real. And again, in a few lessons, we'll learn how to deal with taking the square root of a negative, but for right now, we're just going to say it's not real. All right, let's talk about one more thing here, and this is very important also. So if I have the nth root of a to the n power, it's equal to the absolute value of a when n is even. And if I have the nth root of a to the n power, it's equal to a when n is odd. So this might seem like a peculiar rule, but I'm going to show you why it works in just a moment. So if I had something like the square root of x squared, we've been shown already that we can basically cancel what? The index here with the exponent. So most of you will cancel this with this and just say this is equal to x. Well, that's only true if x represents a non-negative real number. If that's the case, then you're fine. Suppose we had something like, let's say, the square root of 7 squared. Well, if this is a 2 here, this is perfectly valid. You can cancel this with this, and it's just 7, right? 7 squared would give me 49. Square root of 49 would give me 7, so that's okay. But if I had the square root of negative 7 squared, now I've got a problem. If you try to cancel this with this and say this is negative 7, that is wrong. Okay, this is wrong. This is where you need your absolute value. So we would cancel this back and say this is equal to the absolute value of x. So in other words, in this case, it's the absolute value of 7, which is 7. Here it's the absolute value of negative 7, which is positive 7. Okay? Why? Negative 7 squared is positive 49. So if I had the square root of negative 7 squared, this becomes the square root of positive 49, which is 7. Okay, not negative 7. So you're basically doing the squaring operation first before you take the square root. So it takes your negative into a positive, and then it's basically going to give you the absolute value of what was being squared. Okay, so that's how we have this rule. It's very important to understand when you're working with variables what restrictions are there. If your textbook tells you, hey, I want you to assume that all the variables are non-negative real numbers, then go ahead and cancel away, right? In this case, if we have that assumption, you can cancel this with this and say this is x. If you don't have that assumption, then you better make sure you put the absolute value of x, because on a test, the teacher will be looking for that and they'll mark it wrong. So something like the cube root of negative 11 cubed. Well, here I've got an odd index, so I can just cancel, right? It's not an issue, because if I cube a negative, I get a negative, right? So if I take the cube root of that, I would still have a negative. So here I can just cancel this with this, and this is just negative 11, right? So this is no problem, no issue. This is okay as long as you have an odd index. With this guy, I have an even index. So the fourth root of negative 6 to the fourth power, again, I can't just go through here and cancel. What I got to do is think about the fact that this would be equal to the absolute value of negative 6, which would just be 6, okay? And the reason for that is if I take negative 6 to the fourth power, I get 1,296, positive 1,296. If I take the fourth root of that, I go back to 6, right? So I just want the absolute value of this guy that's being raised to that power. That's going to end up giving me the correct answer, right? So please don't just cancel when you have an even index. Let's look at something a little bit more complex, but following kind of the same thought process. So the first thing I want to show you is that throughout the course, you will often see something like the square root of x minus 5. So for this guy right here, we need to figure out where it's defined, right? If we don't want to take the square root of a negative, then we've got to take our radicand here, which is an expression, and we've got to say, okay, this has got to be greater than or equal to 0. I would just solve this inequality. So I would add 5 to each side, and I would have x is greater than or equal to 5. So we would kind of put this restriction and say x is greater than or equal to 5 here. Because if it's less than 5, let's say it was 4. So you would have the square root of 4 minus 5, which is negative 1. And the square root of negative 1 is not real. Okay, not a real number. All right, so down here, we have something that's kind of similar to what we were looking at a minute ago. If we have the square root of the quantity x plus a squared, so some expression being squared here, we basically say that expression that's being squared, we're going to take the absolute value of that for the answer. So let me show you here. If we had something like the square root of x squared minus 10x plus 25, a lot of you know this is a perfect square trinomial. It can be factored into a binomial square. So this is the square root of x minus 5, that quantity squared. And essentially what I'm saying here is that you can't just cancel this with this. It's not equal to x minus 5. it's only going to be equal to that if x is greater than or equal to 5, okay? The case where the result under here is non-negative. And let me show you why it's equal to the absolute value of x minus 5. If x represented a value that gave me a positive here inside the parentheses, let's say x was 8 as an example. So I could plug in an 8 there. 8 minus 5 is 3. Absolute value of 3 is 3. So I know I would get 3 as an answer. So plugging in an 8 there, 8 minus 5 is 3. 3 squared is 9. The square root of 9 is 3. So I'm good to go. If I plugged in something that made it negative, though, think about this. If I plugged in, let's say, a 3. 3 minus 5 is negative 2. So I'd plug in a 3 here. Negative 2, the absolute value of that is positive 2. So this should be my answer. So plug in a 3 there. 3 minus 5 is negative 2. Negative 2 squared is 4. Okay, positive 4. The square root of positive 4 is 2. If I didn't have that absolute value there, think about the fact that if I just went through and canceled, I would just be left with x minus 5. If I plugged in my 3 there, 3 minus 5 is negative 2. So I would have the incorrect answer of negative 2. Okay, so that's why you've got to have those absolute value bars there. It's to include scenarios where this guy ends up being negative, you square the negative, and you get a positive. Then when you take the square root, you've got to involve the absolute value operation. Okay, so very important you understand that. All right, so the square root of x squared minus 4x plus 4, again, we have another perfect square trinomial. I would factor this and say this is the square root of x minus 2 squared. And I could say this is equal to the absolute value of x minus 2, okay? Again, if we wanted to just define this for x being greater than or equal to 2, then we can cancel. So if I put a restriction here and said that x is greater than or equal to 2, well, then I can just go through and cancel. I can say the square root of x minus 2 squared. I can cancel this with this, and I can say this is x minus 2. That's perfectly legal because no matter what, x is greater than or equal to 2. So if I put a 2 there, I get 0. Square root of 0 is 0. So I'm okay. If I put a number larger than 2 there, I'm good to go. I can't put anything less than 2 because that would give me a negative here, and that would result in me having to use absolute value bars. So as long as you put this restriction in here, or the restriction is given to you, then you're good to go. Okay? You don't have to go through and use absolute value bars. But if I take this away, then I've got to make sure that this is the absolute value of x minus 2 to account for the fact that this expression could be negative. We're squaring the negative, we get a positive, we take the square root. Again, you need the absolute value operation for that scenario.